So now let's start the lecture. So first I want to quickly recap two of the things we talked about last week, because these are very important things, so I don't mind repeating them just to make sure you really understood them. So the first thing is to clearly understand the difference between a shielded cable and a transmission line like a coax, although physically they look the same. And as you recall, last time I showed you here in this bundle, the wire with a yellow tip was a shielded cable, like a video or audio cable, okay, typically from audio systems. And the coax, which looked exactly the same, and if you look at the end, they look exactly the same, this was called a coax or a transmission line. So what's the difference if they look the same? So there is a bit of difference in construction, that the coax is made more carefully, more attention to keep the impedance constant, but the real difference is in the way it's used. A shielded wire is used without any consideration to impedances. So any shielded wire, if you take a shielded wire, there is some parasitic capacitance between the wire and the shield. There is actually also parasitic inductance, because any wire, if current flows through it, it means the current has to return somehow. And if current flows through a wire and has to return somehow, you create a loop, and that means there is inductance, okay? So there is also parasitic inductance, although it's not obvious when you look at a wire. Why would a piece of wire have inductance? But it has. So now, but even if we ignore the inductance, there's also a bit of resistance, but even if we ignore all that, if we say this wire is basically a capacitor. So typical shielded wires or typical coaxial cables, they have a capacitance in the order of 100 picofarad per meter. That's kind of a good number to remember. That just comes from the geometry. So when you drive them, let's say you have a source, you have an AC source, has a resistance R. Now you drive this piece of wire, okay, and say you have a load R. This is, so let's call this R0. This is the source, and let's call this RL. And this parasitic capacitance is called C. So what you get is a low pass filter, because if you redraw that, you get R, and here you have C and another R. So this is this piece of wire redrawn as an electrical circuit. This is RL, this is R0. So obviously you get a low pass filter, what's called an RC filter. And you can, so if you change this frequency, it will look like this. Okay, it will have a 3 dB point where the power is half. Does everybody know what a 3 dB point is of a Bode plot? Yeah, good. Okay, so power is half, so it will behave like this. Okay, but if you change the length of the wire, the capacitance will go up. So if you make a very long wire, it will go like this, okay? But it will always be frequency dependent. Now, if you take the same piece of wire and you calculate its characteristic impedance, okay, and the characteristic impedance of a piece of wire which has L, distributed C, the characteristic impedance is square root of L over C, and it comes out in ohms. If you put the units in, you get it, the units come out in ohms. So now, if you take the same piece of wire and you drive it with Z0, so I didn't change the wire, I just using a property of the wire called characteristic impedance. It still has the same L, the same C, I'm ignoring R, but now I'm driving it through a source which in this case is resistive. I'm driving it through a resistor equal to Z0 with a source, and I'm loading it, and I have to load it also as a resistor equals Z0. Now, this wire will behave purely resistive. Okay, so it will behave as if you look through it, you will see Z0. Okay, now because it will behave purely resistive, then the Bode plot, if this is amplitude and this is frequency, it will be flat, totally independent of frequency. Eventually, everything eventually breaks up at very high frequencies. So eventually it will fall down, but this thing will happen at hundreds of megahertz, where everything gets complicated. But here, if I took real numbers, say if I took real numbers here, make it very simple, I take a function generator, and all these things have a Z out of 50 ohm typically, because they're designed to drive coax. Okay? And if I drive it with, say I connect to it 10 meters, just for example, I connect for it 10 meters times 100 PAF. So I connect to it, I'm getting 1,000 PAF load. And let's say this is very high, let's say this is infinity. So that corner frequency, the 3 dB point, I can easily calculate, because the 3 dB point is where this impedance equals this impedance. Okay? That's the definition of 3 dB point. Now please note that because one is capacitive, one is resistive, when this impedance equals this impedance, say ignoring this for a moment, the voltage doesn't fall to half, because the impedances are out of phase. There are two vectors at 90 degrees out of phase, right? You remember that from somewhere. So when the two impedances are equal, the voltage only drops to 0.7, because when you take two vectors and they're equal, okay, this vector is only 1.4 times this, not 2. So because of that, when this equals this, the voltage drops to 0.7, which is a 3 dB point. So let's calculate the frequency when this happens. So if I have 50 ohm and I have 1,000 PAF, so I say R equals 1 over 2 pi FC, because that's the impedance of a capacitor. So F equals 1 over 2 pi RC. And if I just plug in the number, say R is 50 ohm, C is 10 to minus 9 farad, okay? And let's say 6 times 50 is 300, okay? So this will be 10 to minus, so there will be 10 to minus 7 divided by 3, so it will be about 3 megahertz, okay? Because this is 10 to minus 9, okay? This is 3 times, roughly 3 times 10 to the 2, so it's 10 to minus 7, so 10 plus 7 divided by 3 is 3 megahertz. And you can check it later. So this 3 dB point will be roughly at 3 megahertz, while if this was wired as a coax, that point will be hundreds of megahertz away. So what is so important about it? Because you can say, well, you know, I'm only using it to a few hundred kilohertz or a few megahertz. This sounds to me good enough. So sometimes it is good enough, but if you're sending pulses, you have to be very careful. Because when you do something which sends pulses, and there are many things which send pulses, like shaft encoders, or things which send pulses over a long line, especially if the pulses come at kind of random intervals. So you have a shaft encoder where the speed is changing, so you get pulses. Now the spectrum of a pulse, as you know very well, okay, it looks like a single pulse will look like sine x over x, okay, but basically the spectrum of a pulse has many spectral lines, and if these pulses are random, the spectrum will be like something like this. So the high frequencies, in this case, if I superimpose on it spectrum of pulses, the high frequencies will be attenuated and also phase shifted. This also implies phase shift. So when I reconstruct the pulse, when I send a pulse train through this, when I send in something like this, like I drew there, a random pulse train, what I'll get coming out will look like this. Okay, like the fast pulse will come out smaller, and basically the pulse train will be distorted. And the more complex the pulse train, the more it will be affected by the distortion, because different components of the Fourier components will propagate at different delays and different phases. Now if I send a pulse train through this, it will come out exactly the same, maybe with a slight rounding because of it's not infinite bandwidth, but it will come out exactly the same. So the significance of something being frequency independent is not just that you can work at high frequencies, like in RF. The real significance, it doesn't distort the shape of the signal, because it passes all spectral components equally. Okay? So that's why when you send pulses over long distances, and even not just pulses, high frequencies, you have to use this method, like transmission line, versus just a shielded wire. Okay? And because of lack of time, I didn't prove to you that Z0 equals to this, but if you want to prove it to yourself, you do what Heaviside, as I reminded you, that if you have a transmission line which has a Z0, and you add a little section, delta L, so you add the delta C and delta L, when you look inside, it should still be Z0. Okay, and then you write the equation, and then you make delta L equals 0, and then you get this. Okay? So if you're really curious, you can convince yourself with that. So, whenever you put a piece of cable, thank you. So whenever you put a piece of cable, you calculate this number. If this number is high enough compared to your frequencies, you don't need a coax. Okay? But if this number starts getting close to a few harmonics above your frequency of interest, you have to switch to that. You have to use coax. Or you have other choices, lower this resistor. If this resistor is very low, it can drive the capacitance much better. Okay, so there's more than one choice, but basically you have to be worried that the waveforms will be distorted. Okay? Clear? Good. Okay. I also mentioned the typical impedances of coaxes, which are standardized all across the world, is for coaxes it's typically 50 ohm, which is most all of them, and 75 ohm, which is used for cable TV and other things. And for transmission lines which are not coax, because you can make a transmission line just by running two wires, it doesn't have to be coax. For transmission lines which is not coax, the most common one is 600 ohm, where all of the telephony systems in the world are based on. Because this just happened to be the transmission line of two wires strung on poles, right? So the same as this just happened to be the transmission line impedance of a coaxial construction. And then there is also 300 ohm. So these two are used for just twin leads, two wires strung like wires on telegraph poles. And these are used for coaxial wires. Okay? Good. Okay, so these are the four most common numbers. There is also a whole bunch of other numbers, 93 ohms, and a whole bunch of odd numbers, just to make life more difficult. Okay? But these are the four most common impedances of transmission lines in the world. Okay. Now, the second concept I explained last week, which is very, very important, is this concept of shielding, that just because you put something in a metal box doesn't really mean it's completely shielded from electromagnetic interference, the same way that the shield around the wire, this braid I showed you surrounding the wire, doesn't protect it from everything, right? I showed you that in a shielded cable you have a metal braid, and so I explained to you not to assume this metal braid stops all electromagnetic fields. And that's very important to understand, and reminding you of the demo which I gave you last week, that I had a sealed metal box, all metal all around, and it had a coil and an LED inside, and the LED was lighting up when I put it in a 60 Hertz AC electromagnetic field. Right? I had an electromagnet plugged into the 60 Hertz. When I held it next to this box, the LED lit up. And to light up an LED, you need a lot of volts, like 3 volts, in this case, blue LED. So this little box, although it was all metal, there was no problem generating 3 volts inside. So that's very worrying, which means this whole concept of shielding has to be treated with great care. So if you take a shielded cable, or if you take a box, if you're really dealing with very low signals, not any box will stop the signals. Almost any box will stop static fields. Like almost any steel box will stop static magnetic fields, and any metal box will stop static electric fields. But if the field is AC, okay, the electric field causes magnetic fields, the magnetic fields cause electric fields, and the box will stop most of it, maybe 99.9%, but not all of it. Okay? So I gave you an explanation last week which was based on Maxwell's equations. Why is there an electric field always associated with a magnetic field and vice versa? Like the classic explanation is Maxwell's equation, and what happens is that when you have a changing magnetic field, if you have a metal box, and I put a coil here, the coil obviously produces a changing magnetic field into the box. Now, this changing magnetic field will induce an electric field which will cause currents to circle inside the box, but these currents wouldn't be able exactly to balance out the magnetic field. So it will kill most of it, but there will still be some residual field. If this box was a superconductor, it would be a perfect shield, because a superconductor means zero resistance. Now, zero resistance means you cannot have any potential difference, because V is IR, but if IR is zero all the time, you cannot have V. So if this was superconductor, there could be no potential difference, okay, then there would be some surface current, but inside there would be no field at all. But practical materials, if you put steel is good against the magnetic field, but then the steel has high resistivity, so it actually allows quite a big potential difference. If you take copper is a good conductor. It doesn't allow high potential difference, but it doesn't stop slow magnetic fields. Okay? So there is another way to explain this, and this is based on Lenz's law. Now, Lenz's law is a very practical law in electrical engineering. How many people here heard of Lenz's law? Oh, not enough. Okay. So what Lenz's law says that any induced electromagnetic field will try to cancel the source of the induced field. So in other words, what Lenz's law says that if this is trying to induce a current in the box, the direction of this current would be such to create an opposing field, to cancel the reason for the induction. Now, the classic demo of Lenz's law is if you take a copper pipe and you drop through it a piece which is not magnetic and a piece which is magnetic. So if I drop a piece of chalk to the pipe, it falls down instantly, right? Just gravity acceleration. But if I take a magnet and I drop it through the same pipe, it seems to take much longer to come out. Okay? So I'll do it one more time, because that is the most classic demo of Lenz's law. You drop a magnet through a copper pipe, it takes a very long time to come out. Okay, now can somebody explain quickly why did the chalk come out much faster than the magnet? That's physics 101, so yes.
We're talking about Lenz's law, I assume that
I gave you all the hints possible, so
as the metallic piece is falling down,
yeah,
the magnetic flux is increasing in the downward direction, so the currents that are created will have their magnetic fields pointing upwards.
Very good. So basically that's a magnet. As it falls down, it has a changing magnetic field in the copper, because the magnetic field is traveling and changing all the time. A changing magnetic field in copper will induce a current, simply because there is a voltage induced, which is d phi to dt. So this is a voltage induced, and if I divide this by the resistance of the copper, I'm getting the current. By Lenz's law, this current will create an opposing magnetic field which will try to cancel the reason for it happening. Since the reason for it happening is the fall of the magnet, the polarity of the induced magnetic field will be not to allow the magnet to fall. Okay? Is that clear? Good. So that's Lenz's law. So another way to explain this business of shielding, why it's not perfect, is looking at Lenz's law, and we say there is a field B. The field B will induce a current I based on this, but the current I will try to create an opposite field B to cancel this out. However, if this was a perfect conductor, it will manage to completely cancel it out, and there will be no field inside. But because it's not a perfect conductor, it can't achieve full cancellation, and some of the field will go through, because the induced B will be a bit smaller than the original B. It's exactly the same reason as if I drop this magnet through a superconductor pipe, it will never come out. It will just get stuck right here and never be able to fall in. Okay? Because the superconductor pipe will induce an exactly opposing magnetic field. There will be no movement possible, because the resultant field with zero resistance will be exactly equal to the original field. But since it's not perfect, in spite of the Lenz's law, the magnet can fall down, it just slowed down. But if you really took a superconducting piece and dropped it, it'll just stay hanging like this forever. And this is called in physics, what's the name of this effect? That a magnet cannot fall onto a superconductor. That's a test. When somebody says, I made a superconductor, there's a very simple test to know if he's right or not. You just take a magnet and put it above what he shows you, what they show you. If the magnet floats, it's a superconductor. If the magnet drops, it's not. That's a test. That's how something is tested. So what's the name of this effect? What? No, come on, fellows. You learned about superconductivity at some point, right? So what's the name of the effect that a magnet will always float above a superconductor? Meissner effect. Right? It's a basic thing in physics, right? I'm not 100% sure about the spelling, but it's a Meissner effect. Okay, it may be IE instead of EI, but anyway, if you have a superconductor, Lenz's law is perfect. No magnetic field can penetrate. But for most practical boxes, the opposing field created by Lenz's law is not perfect. It's not enough to completely cancel. So some little field will go through the wall. The shielding will not be perfect. Okay, so now you start saying, how should I make the best shielding? I know it will never be perfect unless I have a superconductor, and you quickly realize that if you made it all of steel, it will be good, but the steel is not such a good conductor, so maybe it will help because steel has a high mu. It will be good to make a strong magnetic field, but it has high resistance. There will be a voltage drop. If you make it all of copper, it wouldn't be able to stop very slow magnetic fields, because at very slow magnetic fields the induced voltage is very small, and for a DC magnetic field copper will do nothing. The magnetic field will go through. Right? So what do you do? If copper is not so good for low frequencies, steel is not good for high frequencies. By the way, the reason steel is not good for high frequencies is another reason called skin effect. Okay, how many people here know what skin effect is? Okay, more of you should know. When you run a current through a conductor at low frequency, the whole cross section carries the current. At high frequency, the current is only sitting on the outside and cannot penetrate inside the conductor. So if the conductor was hollow or solid, it'll be the same, because the current inside is repelled by itself to the outside. So basically all the current is repelled and it's only sitting on the skin. Now this effect gets stronger and stronger with high frequency, and at very high frequency the conductor is not good because the penetration of the current is very shallow. So the reason why here the shielding at high frequency is bad is this appears much more resistive than it really is at high frequency because of skin effect. Skin is like human skin, it's not the name of a person, right? Okay, good. So what do you do if iron is bad for skin effect, because in ferromagnetic materials the skin depth is much less. So if iron is bad for skin effect, copper is bad at low frequency, what should you make the box of? Of what?
Both.
Exactly right, both. Since we can decide, make it from both. That's why for high shielding you typically have a steel box coated with copper foil. Now, what is better, to put the steel inside and copper outside, or the other way? Like if you look at these boxes in instruments, it's always copper outside. Why? Very simple, nothing to do with shielding. Steel rusts, copper doesn't. So it's better to put the copper outside so it's protected from rust. Also easier to solder to. When you want to ground it, it's easier to solder to it. So that's a classical way of doing it, and for the connoisseurs, for the people who really like to do a very good job, you don't use steel, you use an alloy which has a very high permeability even at low fields. Because it turns out if you look at the graph, magnetic graph of steel, and magnetic materials are characterized by a graph which is called a BH curve. H is a magnetizing force and B is a resultant field. So typically you've seen these graphs, they look like this for all materials. We'll talk more about it when we talk about actuators. So that's a typical BH curve, and this is a slope. The slope is mu, because as you recall, B is mu H. That's the definition of B. Okay? But it turns out when you enlarge the zero crossing, when you just look at the zero crossing at very, very low H, very low magnetizing force, you see a very strange anomaly. You see that steel actually looks like this. So at very low H, it doesn't work. Only if above a certain age it starts magnetizing. Now, can somebody guess why that is? Why does there seem to be some inflection here near zero, some funny thing? So you have to think about how magnetism is formed in steel. Okay, yes?
You need a normal amount of magnetic moments to line up.
To line up what?
In an orientation to your magnetizing force.
Yeah, but what are you lining up? You are very close. But
the dipole?
Or
magnetic moments.
You basically line up the domains. It turns out that in a material, of course, each atom has a magnetic moment, but it turns out that the magnetic material is built up of many domains. So when you look at a piece of steel and you magnetize it, it appears to have like random zones, and each zone has a different direction of magnetization. Okay, a bit like crystal structure, but the domains are not necessarily on the crystals. Okay, so if it's not magnetized, all these domains point at random directions. If you magnetize it, they turn and orient. But it turns out that you need some minimum magnetic field to turn them. They're like similar to friction. You have to overcome static friction. So this means that if you take normal steel, but nothing will happen at very low fields, so it wouldn't be able to shield from very low fields. So there are special alloys developed which don't have that, which go like this. Okay, so this is regular steel. And there are special alloys, and the most known of them is called mu metal. Mu metal is a trade name, but it's also known by the generic name mu metal. And this alloy goes through zero and has full permeability at zero field. So the mu metal has very small domains and easy to rotate, doesn't have this problem. So if you want to, yes please.
Saying that as you apply magnetic field to iron, inside of it, these pieces are mechanically like actually moving around?
Okay, they are not mechanically, but the magnetization of them is moving around. So, see what? Okay, let me explain this again. The magnetic domains are not the same as crystals. There is some zone which is magnetized this way. It has a boundary, and another zone magnetized this way, but it has visible boundaries. For example, if you take very fine iron powder and sprinkle on this and look at the microscope, you can actually see the boundary, because the same as iron powder will line up between two magnets at the boundary, it lines up on the domain boundary. So these are actually visible to the eye through a microscope. Now as you magnetize it, these boundaries start shifting. So there is some mechanical movement as well. Okay, and this is easy to prove by the fact there is such a thing called magnetostriction. Do you know what magnetostriction is? If this is a piece of steel and I magnetize it, the length changes. So it means something mechanically has to move inside too. You know, when you walk near a power transformer, you can hear it humming. Right? This is magnetostriction. The whole transformer is growing and shrinking 120 times a second. So there is actually a mechanical movement too, but anyways, all this getting too detailed for the time we have. So read up on it, read up about magnetic domains, magnetostriction. But so there is some physical movement, but what really happens, the most noticeable effect, the boundaries of these domains change and the orientation of the domains change. It doesn't mean the domain is physically rotating, but the boundaries there, where the magnetic lines separate, shift, and they line up, they all line up. Okay, it's actually not a simple effect. There's a Barkhausen effect, which is a jumping of the domains. There's a whole bunch of effects there which take place. You can read up on it. But the interesting thing, all these effects are visible. You don't need fancy labs to see it all. Okay, so this Barkhausen effect is the effect that don't move smoothly, that they jump. Okay. So bottom line is that shielding is not such a simple story. Sometimes you have to build a special box with two metals, with the right metals, if you're dealing with very low signals. Okay, next subject. So all this basically was a review and a bit more of last week's lecture. Any questions about that? Good. Okay, next subject we're covering is grounding. Now grounding is sounds like an intuitive concept, that you take the shield, or you take this shield, or you take the box, connect it to ground in order to ground all the bad signals, all the interference. But to my surprise, I find out that most students don't even understand what this ground wire and what the neutral and phase are connected to in their own house. So they don't understand the grounding because they really don't know what these wires are connected to. Okay, so let's go over this quickly, because if you don't understand how your electrical system in your house works, you can't understand what the grounding does. Okay, so can somebody explain, in a regular house, you have some appliances which work on 110 volt, like all the lights and everything, and some appliances work on 240 volt. Right, so in a normal house, if you look at an apartment or a house, you look at the breaker box, it says 120 volt, 240 volt, typically says 100 amp, says this is the breaker box in an apartment, and in a house it'll say 200 amps. So how is there in a house both 120 volt and 240 volt? Can somebody explain? Yes?
240 coming in off the transmission lines, and then they split it apart.
How do they split it apart?
Just use the volt, just divide the voltage divider.
No. Okay, yes?
You have to phase 100 in, if you phase out 103 volts.
Okay, good. Okay, so first surprise is most people don't even understand how the house wiring works. How do you have 120 to 8? So the way you have the two voltages, in a house you have a neutral coming in and two phases 180 degrees apart, which each one carries 120. Okay, there is actually no 240 coming into a house. There's only two phases 120. One phase looks like this, and the other phase is the opposite. Okay, so this is usually black, neutral is white, and this is typically red or blue, and there are two phases apart. So if you look between the two phases, you get 240, because when one is plus 120, the other is minus 120. Okay? If you look between a neutral and a phase, you get 120. And that's how all the breaker boxes work. If you look inside the breaker box in a house, okay, the way it works, you have two phases. You have in the middle you have some bar, which is a neutral, and then you have two phases, and the breakers take it alternately. So the first breaker takes neutral to one phase, the second breaker takes neutral to the other phase, to load both equally. If you want 240, like for a kitchen or a dryer, you take it from the two opposing phases. Okay? The way you generate at the transformer outside your house, the way you generate these two phases, you have a transformer where the center tap is neutral, So this is phase 1 and this is phase 2 of 120 volt, but the transformer is wired that this end is opposite phase. So you have 220 volt between the ends of the coil, but relative to ground you have plus 120, minus 20, and then it reverses. Okay? Now, in a house you also have a ground wire. Okay. What is this? What is this ground wire connected to? To ground, yeah, basically somewhere it's to pole, to a pipe, into the ground. Now, when you take an ohm meter, when you shut down the power to your house, let's say the house is not powered, and you take an ohm meter and measure between the neutral and the ground, what resistance will you get? Is the neutral isolated from the ground or not in a house?
Open circuit.
Pardon?
The open circuit.
Okay, how many people say open circuit? And how many people say short between the neutral and ground? It's the same story every year. Of course it's short. The neutral and ground are connected together. It's one wire outside the house. And if you ever try it, you'll see. But you cannot not try it with... You can try it with power on, because neutral doesn't have any power. Okay? So you can actually try with power on, but just to be safe, don't try it with power on in case you plug in the ohm meter at the wrong place. But anyway, I'm surprised every year that not just you, but electrical engineers, none of them understands how the house is wired. Okay, they graduate with a diploma in electrical engineering. Out of a class, maybe one ever understood how his house is wired. Okay, it's very worrying. But anyway, but at least you can graduate from here without understanding sensors, but I think you shouldn't graduate from here without understanding how your house is wired. Okay? So that's how your house is wired. Now the neutral is connected to the ground outside your house. Okay, inside the house are two separate wires, but if you measure with an ohm meter, it's the same wire. So this point of the transformer outside your house is actually connected to ground. Okay, now the last question: why is the neutral connected to ground? Wouldn't it be better to keep it separate, just for safety or whatever? Like when you have a battery, no side is connected to ground, right? So why in a house is the neutral connected to ground outside the house? Okay.
Safety precaution.
And why does it increase safety?
So when you connect them outside, you basically dissipate your load out through the dirt.
No. See, be practical. You know that for safety, appliances have to be grounded. Although today there are many appliances which have a two-prong plug, because they don't have to be grounded, because you can't get electrocuted, because it's all plastic. So if you have a hair dryer or something like this, it's all plastic, so there's nothing to ground anyway. There's no metal, so it has a two-prong plug, like a stereo. But everything else has a three-prong plug, right? Like a fridge, a motor, a hand drill, everything is a three-prong. So obviously the ground is needed for safety, because things made of metal have to have a ground and a three-prong plug, right? So how does it increase safety? Yes?
Because when you use that appliance, you're standing on the ground.
Yes, but why does this connecting the neutral to ground increase safety? We agreed that the appliances are grounded to increase safety, because that's how it looks. Everything you buy which is bigger has a three-prong plug. But why? What does this have to do with this connection between the neutral and ground? Yes?
So if the metallic casing is shorted too high, the current doesn't pass through you to weaken the ground, it passes through the ground.
You're very close. You're very close, but it's not a full explanation. Okay. What you want to do in a house, that if there is a short in the wiring or a short in the appliance, which makes the case, the metal case of the appliance, go live, you don't want it to be allowed. You want to blow the breaker, right? Otherwise, when you touch the case, you'll be killed, because you are connected to ground. If the case of this computer will be touching the live wire, if I touch the metallic part, the current will go through me to ground. Okay? So I don't want to allow the case of anything metallic to become live. Live meaning have a potential of ground. So the way it's done, so you come into the house and you have the breakers, okay? So this is phase 1, this is phase 2, this is the breakers in your house, in the breaker panel, okay? Now you have the neutral, okay? And now you have a load. Let's say you have a load, or is there a load between those? If it's but basically this is your load. Now the load sits in a case, and the case is connected to ground, which is a third in your plug. If you look in your outlet, it looks like this, and this. This is your outlet, this is ground. So the case is connected to ground. Now, if the neutral would not be connected to ground, if the live will touch the ground, nothing would happen. But if the neutral is connected to ground, okay, if the live wire will touch the ground, if this live wire by accident will touch the ground, not this, the live wire, if the live wire by accident will touch the ground, because the ground is connected to neutral, it will be the same as the live wire touching the neutral. And the live wire touching the neutral is a short. And if you have a short, the breaker will blow, or the fuse. Is that clear? So if you don't connect the neutral to ground in a house, okay, outside the house, inside you cannot protect yourself from the cases of appliances becoming live and electrocuting you. Okay? Okay, now this, as I said, you shouldn't really graduate if you don't understand how your house is wired. So is there anything with any question about this? Good. In industry it's different. Industry runs on a three-phase system, which we'll discuss when we talk about motors. But households run like this. Okay? So, and if you have, like, let's say you have a thing which works on two phases. Let's say you have an oven or a dryer which works on two phases, it will still work. Although it doesn't use a neutral, if the case of a dryer will touch live, although it doesn't use a neutral, it will still be like shorting the ground to live, and the ground is the same as neutral, so it will be still a shorting the ground to neutral and blows the breaker. So you don't need even the neutral wire for this system to work, but the neutral has to be grounded outside the house. Good? Okay. Now, so what that means that all the currents, all the return currents in a house coming through the phase, return through the neutral, or coming through a phase and return through the opposite phase. So there should be no currents in the ground. But there is always some leakage. What happens if there is no short, but what happens if there is some parasitic resistor like this? In other words, the insulation is not perfect. So this is our insulation. So it's not intended to touch the ground, and if it touches the ground solidly, or the case, it will blow the breaker. But what happens if it's just some leakage? And this happens because insulation is not perfect, and all the appliances in the house add up in parallel here. Right? Because the neutral and the phase go through the whole house, and each appliance has a bit of leakage. So it adds up to some current. So there is actually some return current through the ground because there is some leakage through the insulation. This leakage is connected to the ground, and this current flows all the way outside the house because it wants to return to the neutral. Okay, this current can be significant. Like the electrical code says that this has to be larger than 1 megohm. Okay? So in other words, when you build a new house, they're supposed to come and take a a resistance meter, and check if the insulation is good. But after that, you buy all kinds of appliances, nobody checks. Right? You can plug in an old fridge, an old drill, it can have much bigger leakage than that. If the leakage has to be huge to blow the breaker, because this breaker is rated 15 amp minimum. So you can have a leakage here of amps and you will never know if you have bad insulation. Okay? So because of that, it means that the ground wire, which is not supposed to carry any current except in an accident when it's shorted, actually carries some leakage currents. And that has a very bad consequence, that if you take the ground in this room and you take the ground at this end and you take the ground at that end and the ground at that end and you measure the difference with a voltmeter, the three grounds will not read exactly the same, because these leakage currents flow through the ground, through the wires, and there is some voltage drop. So I would expect, if I measure the phase between two outlets or the neutral, I would see a small difference. Because the reason I'd expect this, because in a house, if the phase comes in, there's many outlets, and the phase is connected to one side and the neutral is connected to the other side. This is phase and this is neutral, and there is some current flowing which could be quite heavy, so there will be some voltage drops. So this will be delta V. So I would expect that between outlets I can see small delta V's. And the best example, when you turn on your toaster, the lights dim. In especially old houses, lights dim, which means must be delta V. Right? 10 volts at least. So I expect delta V between outlets, I expect delta V between neutrals, because it's the same as a phase, the same wire. But I didn't expect that the ground, which is supposed to be 0 volts, I didn't expect that there's also little delta V's along the ground because of leakages. There's all kinds of leakages to the ground which cause small currents to flow through the ground. So that means when you ground things, you have to be a bit careful, because you have a sensor and a computer at two ends of the room. Sensor is grounded to this outlet, computer is grounded to that outlet. You can actually have some currents through the ground. So ground is not truly 0 volt. And that is the reason why in very sensitive systems, sometimes you don't want to ground different parts to different grounds. You want to bring all the grounds together and then take one wire to ground. So if you have a system which has several boxes, okay, let's say, just a minute. You have a system with several boxes. Let's say you have a sensor, and you have a, let's say, a controller, you have an actuator, and each one has a power supply, okay? And this is a ground. So one way to do it is each power supply is plugged in and the box is grounded to the ground. But sometimes this is not so good, because if it's different rooms, the ground is not exactly the same. Okay, so sometimes you actually want to do this, not to ground here, but take this wire and bring it to here, and not to ground here, take this wire, bring it to here, and have one common point. Okay, so then all these three boxes are really at the same potential. Okay? And this is called common point grounding or common ground. Sometimes it's also referred to as audio style ground, because in audio amplifiers inside the parts are grounded this way. Because an audio system is very sensitive to picking up hum, because 60 hertz of the audio system, you can hear it. It's an audible So, and this can happen if you, inside the audio system, you have multiple grounds. So inside, if you have a big audio amplifier, they do this. They bring everything to one point. Okay? So that's kind of single point grounding, or central point grounding. Okay? But there's a catch. So this works well for 50, 60 hertz, maybe up to a kilohertz, or maybe a few kilohertz, depending on the need. But there is a problem here, because these wires can be very long. If you have a sensor and an actuator spread all across the room, these wires, to bring them all to one ground, can be very long. And the problem you run into at high frequencies, this can be a fraction of a wavelength, or more than a wavelength, and then you can have 0 here and maximum here on the same wire. Because I mentioned before standing waves. When you have a piece of wire, and this piece of wire is half a wavelength in length, you can have an electromagnetic field which is 0 here, and maximum in the middle. Right? Just like a string of a violin. It can move in the middle and not at the ends. So if these wires become a significant part of the wavelength, the system doesn't work well. And you're better off trying to ground the shortest path anywhere. Okay, so another style of grounding is, especially if you have a big metal enclosure, ground everything to the metal in the nearest path possible. So let's say you have a big metal case and you have all kinds of boxes inside. You ground each box to the nearest path possible, and this is called RF style grounding or multi-point grounding. So this thing is called or sometimes referred to as RF style, because all RF systems are grounded like that. So if you take apart your cell phone, you take apart anything which deals with RF, your router, the internet router, there is some ground plane and everything is connected to the ground plane. Okay? Because the frequency your internet router, wireless router works is very high. It's hundreds of megahertz, so the wavelength is very short. So you certainly cannot run long wires to central ground. So there is no hard rule when you use this grounding, when you use this grounding, but as a general rule, at a few megahertz you can't use this anymore. Because the general rule is if the dimension is such that L is larger than lambda over 100, then you have to treat it as RF. It's not a mathematical hard proof, it's just a rule of thumb. Because if you have a sine wave, and this is lambda, at 1% of lambda, there is already a significant voltage, because 1% of lambda is 3.6 degrees, right? 360 degrees, 1%. 3.6 degrees, sine of 3.6 degrees is probably 0.05, it's around 5%, right? Because do it in radians, 3.6 degrees divided by 56, so let's say it's 15th of a radian, okay, so this would be about 6. Roughly, you can look it up in your calculator, but if this is 1% of the wavelength, this is going to be like 5-6%, so it's already significant voltage. So that's why this is kind of a good guide. If you're dealing with items or wires which are 1/100th of the wavelengths or more, you have to treat it as RF. So there are different rules of design. See if you're fully awake until now. In your bathroom there is something called ground fault interrupter. In your bathroom there are some outlets that besides the normal 2 outlets there is a little red and black button. That's test and reset. And this thing is supposed to protect you from being electrocuted, especially in bathrooms where you're very sensitive that they're wet. So if you touch something, you touch the electrical wire or something leaks electricity, this will shut off the outlet. So this thing is called a GFI, which stands for ground fault interrupter. You buy it for $10 in any hardware store. How does this work? How does this know you're getting electrocuted? So if you listen carefully, a minute to think about it, you should be able to explain how it works. So, how does a GFI switch work? Yes?
It ensures that the current going to the neutral and live are the same.
Very good. Very good, because if you don't get electrocuted, this is phase, and this is neutral, and this is your load. If you don't get electrocuted, the current coming in as a phase and current coming in the neutral must be exactly the same. Now if you get electrocuted, there is some current flowing to ground. Okay? So if some current flowing to ground, I should draw it on the live side here. If some current is flowing to ground, and let's call this delta I, could be small, could be milliamps, then if this is I, the return current will be I minus delta I. Okay, so if these currents are not exactly the same, somebody is being electrocuted, or there is leakage to ground in the appliance, which is also bad. Shouldn't be used in bathrooms. So how does it physically, this is a very small difference. Typically the GFIs are set for 5 milliamps. That's the code. And this is actually 15 amp. Because the outlet will give you 15 amps. So how can it detect a 5 milliamp leakage on a 15 amp current for $10? Because it's a very simple thing. You can buy it in any hardware store. If you were to design it, now it's back to sensors. If you were to design a sensor which can detect a very small difference between two big currents, how would you do it? Yes?
I would run coils around the phase wire, and then I'd pick up. Then you can induce a current through that, and then you can use that current.
So you're saying you put some coil here which picks up the current here,
Yeah.
and then how would you pick up this current?
Probably do the same thing. Then
Okay, so you have another coil here which picks up this current, and then what?
take the difference between the two.
Good. Now that is correct. There is a simpler way actually. But the simplest way is yes. Not so simple, because you really want to measure currents here, so it's not so simple to set up a Whitson bridge. But I think the way it's done, which is it's a bit simpler, what you do is you take the current which comes in and you put the wire, this is the phase, this is the current going in, you put it together with the wire which comes back, this is neutral. So you have a double wire, and now you take this double wire and you wind it as a coil. So you take this double wire and you wind it as a coil, maybe just like 5 or 10 turns. And now you put an iron core, like a relay. Okay? Now, the two currents exactly cancel out normally, so this piece of steel is not magnetized. Now, the moment there is a small difference, say 5 milliamps, it will be the same as running 5 milliamps through the coil. But since the coil can have several turns, it amplifies the effect. Typically, it would have 10 turns, it's like 50 milliamp turns, and that is enough to pull an armature and trip a relay which disconnects the phase. Now, this is how it used to be done until about 5 years ago, but 5 years ago they got lazy making the coil, so it turns out it's cheaper to do it in a complicated electronic way than just winding the coil. So if you open the old ones, that's what they have inside. If you open the new ones, they have one turn and they have some much more elaborate magnetic field sensor, which senses the magnetic field is zero, like a Hall effect or something. But the principle is the same. The principle is you run the two wires as one wire, it should have no magnetic field as long as the currents are equal. Yes?
If putting the two wires next to each other, they're still like, because of the distances between them.
True, but luckily when you wind it, it doesn't matter, because like I explained with LVDT, because luckily in electromagnets, if you wind the term here around, okay, it doesn't really matter where you put the term, it wouldn't change the magnetic field. You can move it back and forth. So even if you had on the same rod two separate windings, it'll still work. If you have one winding for the phase, and even if you had a completely separate winding for the neutral, as long as it's on one flux path, it will still cancel out. So it's not important if the wires are really close or not. Just because a nice property of magnetic fields, that if you have a piece of steel inside, it will channel all the fields of the steel, just like the explanation why in an LVDT it doesn't matter laterally. And that's what makes it work so well. So you don't have to do it carefully at all. In terms of radiating some field outside, it's important to put the wires close together. But in terms of magnetic field, if you have a piece of high permeability, this magnetic field is not affected at all by the way it's wound. Even if one winding is much bigger, let's say one winding is bigger, it has very little effect. There is some leakage field which escapes, but it doesn't have to be that carefully wound. Okay? Any other questions? Good. Now, the same thing I explained about the lambda over 100, the same thing I explained that when you deal with grounding, if the dimensions become a fraction of the wavelength, you have to be very careful. The same thing applies to building boxes for shielding. Because let's say you want to make a box, and the box has a cover. A shielded box has a cover with 4 screws. But if you're dealing with very high frequency, this may not be sufficient, because the 4 screws will guarantee electrical contact where the screws are, but there may be no electrical contact here, so it will be the same as having a slot. And if that slot is big, it can act as an antenna. An electromagnetic field can come out. So basically any kind of holes or slots or distance between screws, which is same as grounding points, this dimension L has to be smaller than lambda over 100, otherwise it doesn't work. Because anything which is not continuous ground can act as an antenna. Now again, I don't want to get into electromagnetic field theory right now, but there is such a thing as a slot antenna. Or even think of the dipole antenna. I mentioned in a cell phone, in the old days cell phone, which had an antenna. This was a lambda over 4, and what's called a dipole lambda over 4 antenna, a monopole lambda over 4 antenna. And the way it works, the bottom is grounded. Actually, the best example is your car radio. Look at the cars. Every car has a car radio and has an antenna. Or the old cars, you could see the antenna wire. Now this antenna is grounded at the bottom, but still has full potential at this end. Otherwise, it wouldn't pick up anything. Right? Because that's a standard lambda over 4 antenna. So basically, when you deal with RF, if one end is grounded, it doesn't guarantee the other end is grounded, because you can have a standing wave. So because of this, if you have things like this, it's grounded here, it's grounded here, it doesn't guarantee the middle will appear grounded. Okay? So to make a shielded box, no openings, including slots in the cover, can be bigger than lambda over 100. And this is the reason when you deal with an audio amplifier, when you look at an audio amplifier, it looks like this. It has maybe 4 screws on the cover, but if you ever look at an RF amplifier, because you can buy modular RF amplifiers, okay, they have maybe 50 screws. They have a whole bunch of screws all around the cover, and they have no ventilation slots. They may have fins, like a heat sink, but they have no slots for ventilation. Because everything has to be solid metal, and the cover has to be held down with many, many screws, so there are no gaps. And actually there's even a gasket underneath which conducts electricity. So even between the screws, there is full electrical connectivity. If you ever open some RF stuff, you see this gasket. Sometimes it looks like this. It's a flexible metal fingers which are compressed, and sometimes it looks like conductive rubber, silver colored rubber, which is actually silver filled silicon rubber, so it makes continuous electrical contact. Now the same is true when you connect the shields. When you have an audio box, you have some plastic connector and a wire comes in, but this around the plastic, it's not grounded, or the plastic. If you have an RF box, you either have some B and C connector, which is shielded all around, it's metal, or if the wire comes in, you'll see the wire will come in with a braid, but the braid will be soldered to the box or to a fitting. So it's all metal, it's all covered with metal. Okay? You probably see it in the labs. I can't point out an example in your home because you don't have anything in your home. like this. Maybe the cable TV distribution amplifier, it's done like that. But the boxes have to be all sealed, no slots. Okay, so this is, remember when this only starts showing up at tens of megahertz. So usually servo systems, sensors, you don't run into this problem because you typically work at kilohertz, not at megahertz. But sometimes you have a sensor which transmits wirelessly, and then you have to worry about this. The other type you have to worry about it if you use CCD cameras, because CCD cameras have a very high data readout rate. So maybe the camera only takes 30 frames a second, but each frame of the camera is a megabit, right? A normal webcam. So it only takes 30 frames per second, but it's times 1 megabit. So if you send out the data serially, you're dealing with 30 megabit per second. So you're dealing with tens of megahertz. So any system where you have a CCD camera, although the refresh rate is very slow, the data rates and the frequencies are very high. So you have to, a lot of times, follow a lot of these precautions. So if you have low signal level, low signal to noise, okay, like night vision or whatever. Okay, so is that part clear to everybody? Good. You also notice that in RF boxes, sometimes the box itself is silver plated or made of copper. It's made of, not of steel, it's made of a good conductor. For the normal things it's made of aluminum. For very high-end things it's made of copper, sometimes silver plated. Okay? Now why, if you look inside RF components, in the high end, everything is gold plated or silver plated. Now why is it, for you, inside your cell phone, for example, the RF part is all gold plated or silver plated. Why does it have to be, can somebody think, why not enough to make it from a good conductor like copper? Why does it have to be gold plated or silver plated? There's many reasons actually, but let's hear some. You know what I'm talking about, right? If you look at high-end connectors, even a BNC, if you look even a BNC, if you look at the inner pin, it's gold-plated. But any high-end connectors, not just for RF, are gold-plated, but in RF stuff, when you open up high-frequency equipment, everything is silver-plated and gold-plated inside. Yes? Pardon? Okay, number one, corrosion resistance, because gold protects it. What's second reason? Silver, by the way, is not so good for corrosion, but gold is the best, yeah. So number one, corrosion resistance, you want good contact. What's reason number two?
Does gold have a much lower resistance than copper?
No, gold actually is a poorer conductor than copper, because the best conductor is silver, the next best conductor is copper, and gold is below copper. So roughly, it will be gold, and then be aluminum, say. So gold is, but gold has some very unique property as a connector. Yes?
I'm kind of guessing the surface roughness, like you have better connection.
Not the surface roughness, but you're getting warmer. Yes?
It's more malleable, so it can conform to...
But copper is just as malleable. Gold has a unique property in connectors, because gold needs zero pressure to get a full contact. Every other metal needs a little bit of pressure, because every other metal has a layer of oxide on it, which could be an atom thick. So if you just take two wires and touch them together with no pressure, even two copper wires, unless you apply some minimal pressure, say a gram, there would be no electrical contact, because there is some oxide layer, hydrocarbon layer. Now gold is the only metal which at a very light touch gets full contact. And corrosion resistance means it's never going to corrode. Okay? So the second reason is gold is the best material in making good contact at low force. But there is a third reason, because silver is also good for that, But there's a third reason, especially why it's all silver plated. If you take apart some microwave equipment, it's always silver plated inside. So I understand gold we discussed, but why is everything silver plated in microwave equipment? So a hint, it's related to an effect we discussed half an hour ago. Yes.
Skin depth?
Very good. Okay. Finally somebody is fully awake. Okay. So remember, at high frequencies, when you have a conductor, the current doesn't flow through the whole conductor. It only flows on the skin, and the depth of the skin is a function of the frequency, of the dielectric, and of the magnetic constant. So since metal is not dielectric, it's not magnetic, it's basically just a function of frequency. So it turns out when you plug in the numbers in the formula, if you have a copper conductor and you're dealing with a gigahertz, the skin depth is going to be only microns. So all the current is carried just on the surface. So you put a thicker conductor, it doesn't help at all. So this has two immediate conclusions. Conclusion number one, plate the surface with silver because the current only flows on the surface anyway, right? And conclusion number two, don't use round conductors because if the current only flows on the skin, you're better off to use like conductors which have a much bigger surface area, like a strip, because for the same amount of metal, this has a lot more skin. Okay? So that's why when you go inside high frequency equipment, the conductors are not round, they are strips and they're plated with silver. Okay, so anyway, this ends as a thing for today. I urge you to make sure you really understand this house wiring, grounding, GFI, because this is some knowledge that you need for the rest of your life, even in your own house. You have to understand how the electrical thing works. Thanks.